Numerical simulation of flow through settling basin, a case study of Budhi-Ganga Hydropower Project, BHP. Abstract: an attempt has been made in this study to check the adequacy of the trap efficiency on the deposition amount, movement, and pattern of the sediment using three-dimensional computational fluid dynamics, CFD, on a settling basin of Budhi-Ganga Hydropower Project, BHP. The prediction of the amount of sediment deposition, its movement, and deposition pattern is necessary during the planning, designing, and implementation phase of the hydropower projects, as sediment particles larger than a certain size can cause erosion and damages to underwater machines. 4 different cases with 7 different particle sizes: 0.8125 mm, 0.4375 mm, 0.2325 mm, 0.1975 mm, 0.15375 mm, 0.10125 mm, and 0.075 mm, has been taken during simulation. Trap efficiency for different particle sizes has been compared, and trap efficiency of 99% was achieved for the particle size 0.2 mm from numerical simulation, which is a 13% deviation with the result obtained from physical modeling. Keywords: settling basin, deposition pattern, trap efficiency, CFD, flow 3D. Introduction. The continual tectonic elevating of the major mountain ranges and consequential down-cutting of the river system has caused a high natural erosion rate in the Himalayan region. 1. The withdrawal of water from sediment-carrying river for the development of hydropower is a big challenge. The water withdrawn directly from such a river reduces the capacity of the conveyance system and cause erosions and damages to the underwater machines such as turbine, valves, governors, etc. This causes the operation and maintenance problem that ultimately affects the economics of the generation too. Thus, settling basins are designed to remove suspended sediment particles greater than a particular size that settles down and deposits sediments on the bottom, and they are flushed from the settling basin by certain approaches. The study of efficient operation of settling basin, its performance, and periodic removal of the deposited sediments by water is a challenging job. To deal with sediment-related problems, the prediction of the amount of sediment deposition, its movement, and deposition pattern is necessary. These predictions during the early stage and after the implementation of the project provides the best direction for the planning, designing, or improvement of the project that ultimately optimizes the cost of the project. The settling basin is designed to decrease the mean velocity of the flow by increasing the cross-sectional area, broadening its width, and depressing the floor, that reduces the turbulence level in the water flow and permit the sediment particles to settle. The settling basin is designed in such a way that it settles the smallest diameter of grain sediments in the vertical plane at the bottom of the pool before it reaches the end of the basin. The trap efficiency of a settling basin is defined as 3 equals dash. Where is the trap efficiency of the settling basin? CIN is the concentration of sediment at inflow, CUD is the concentration of sediment at outflow. The design codes for a settling basin are mostly based on empirical approaches that may not provide accurate results, as there is strong impact on the water velocity distribution and the degree of turbulence in the settling basins, that is due to different geometry and inflow conditions 3, 4. Thus, to provide accurate result, certain site-specific modification is required. The effect of the geometry is difficult to execute in 1D parameters in the analytical approaches. Owing to the complicated nature of flow dynamics of water, the functioning of headworks and settling basin is examined by physical modeling and numerical modeling. Physical modeling is developing a scaled physical model based on a similarity theory, whereas numerical modeling is the process of appropriately developing a mathematical model/replica for a complex physical reality that enhances engineering judgment with the power of the digital computer. 5. The physical model test is costly as well as time-consuming, and on the other hand, numerical modeling has certain advantages over physical modeling such as scale effect, cost, time, and interpretation. Full dynamic similitude cannot be achieved by avoiding scale effects in hydraulic models, and the turbulence level in the scale model are significantly lower, which culminates in the overestimation of the viscosity and the surface tension effects when simulating free surface flows over hydraulic structures using the fruit similarity. 6. Further, numerical modeling can overcome various problems related to hydrodynamics and can process small details that may be difficult or be omitted in a physical model. 7, 8. Hannovic, Abhadidruj, et. AL3 used *CCMN for modeling of settling basin of Lower Manang Marsayangdi Hydropower Project, 144 MW, and the result is compared with a physical model that has been built at the Hydrolab Private Limited Demi Harlan, Danj K. Natakusuma, et. AL8 has done settling basin modeling using Flow 3D of Karay 7 mini hydropower plant located in Pasir Melaya village, Silokian sub-district, Samalangan district, North Sumatra, Indonesia. Vishwavijaya Shresth 9 used SIIM 1.0 on the settling basin of Mykola Hydropower Project, Nepal. Thus, attempts have been made in this study to assess the flow in the settling basin by CFD to estimate the trap efficiency of the basin. The result obtained from the proposed modeling was tested with the physical modeling result of the settling basin of Budhi-Ganga Hydropower Project, BHP, 20 MW, Akkam, Nepal. The performance of a settling basin is mainly governed by the geometry of the basin. 10. Further, the modified cases, I removing divider wall in each hooper, case I, and 2 changing transition angle to 8 degrees, case 2, and 12 degrees, case 3, of the proposed settling basin with different size and shapes were analyzed with deposition pattern and sediment trapping efficiency. 2 materials and methods. A technical data of the project. The technical data of BHP 20 MW are gained based on the project report. BHP is located in Akkam district of Nepal between 29 degrees 15 minutes 30 seconds and 29 degrees 18 minutes 35 seconds latitude north, and between 81 degree 1400 and 81 degrees 17 minutes 50 seconds longitude east on the Budhi-Ganga River, a major tributary to the Seti River. The site location map of BHP is shown in Figure 1. The analysis in this study is fixated on the settling basin of BHP. The physical modeling of the settling basin has been carried out, and these data are used in our computation and analysis. 1. Physical feature. The intake is designed to withdrawal design discharge of 26 m3/s at the normal operating level of L. 720 m, 22.1 m3/s for power generation and 3.90 m3/s for flushing. The discharge from the intake is conveyed to 2 settling basins through 2 D-shaped feeder tunnels of 2.5 m x 3.0 m size 11. The feeder tunnels operate under pressure flow conditions. The settling basin of a 9 m long desilting chamber is proposed to remove suspended particles of 0.20 mm. A basin has 2 chambers, each having a flushing channel with bottom width 1 m and a transverse slope of 1:1 on both sides. The plan of the conveyance system and the cross-sectional view of the settling basin are shown in Figure 2 and Figure 3 respectively. 2. Inflow and outflow discharges. The model was run for a single settling basin with 712.0 ml. At intake and a discharge of 13 m3/s was feed. The outflow discharge of 11.05 m3/s and 1.95 m3/s is maintained in HRT and flushing respectively. 11. 3. Sediment data. The model was run for 2000 ppm, out of which 2.40%, 4.50%, 38.10%, and 55.00% of sediment 1.00 to 0.25 mm, 0.25 to 0.10 mm, 0.180 to 0.075 mm, and below 0.075 mm respectively. 11. 7 different particles were used to represent the range of sediments. B. Mathematical formulation. The equations of motion for fluids are solved with the volume of fluid, VOF, method numerical techniques. The Cartesian coordinates, x, y, z, system is used to solve the differential equations that are formulated with area and volume porosity functions. This formulation, called favor for fractional area/volume obstacle representation method, is used to model complex geometric regions. 1. Governing equation. The main equations used in this simulation are the mass continuity equation, the Navier-Stokes equation, momentum equation, and the sediment scour equations 8, 12. The general mass continuity equation for incompressible fluids is plus. See numerical model. 1. Model geometry. The geometry is constructed as per drawings for the base case, proposed case, settling basin of BHP by assembling solid geometric objects as shown in figure 4. Similarly, the geometry is constructed for the modified cases by removing the dividing wall in each hooper, case I, and changing transition angle from 10 degrees to 8 degrees, case 2, and 12 degrees, case 3. In the cases, the transition length for base case and case I is 27 m, whereas for cases 2 and 3 are 34 m and 23 m respectively, and other dimensions are the same for all cases. Figure 4, 3D view of the settling basin in BHP. 2. Model mesh block. The multiple mesh blocks are created to efficiently mesh the model flow domains. According to geometry, 6 mesh blocks are defined. The mesh size adopted for the present study are as follows. The opening conditions in the simulation are defined in initial conditions. In the model, it is supposed that the settling basin is initially filled with water. Areas of fluid are defined using fluid regions. Water at 20 degrees Celsius from the fluid database is used. The acceleration due to gravity is set to 9.81 m/s2 in downward z direction. The renormalization group, RNG, model was selected for the viscosity and turbulence model, as it defines accurately to low-intensity turbulence flows and flows having strong shear regions. Van Ryn equation is set for the bedload transport rate equation. D. Physical model. The physical hydraulic model test of BHP was conducted in Irrigation and Power Research Institute, IPRI, Amritsar, Punjab, India. The descender model was constructed to a geometrical scale of 112, which includes feeder tunnel, descender, and sediment flushing channel. The model was run with sediment load at intake as 2000 ppm for 1 hour, 3.46 hours in prototype. The sediment sample deposited in a different section of the settling basin was collected and the efficiency of the basin was obtained. 11. 3 results and discussion. The velocity vector is used to view the correctness of geometry, and velocity distribution at different sheanage are viewed along with the turbulent dissipation rate. The trapping efficiency for different sizes of sediment particles and sediment concentration distribution over the settling basin with respect to time is computed. The result shows that sediment concentration level is greater at entry and sediment concentration level goes decreasing on downstream. Similarly, sediment concentration level is greater at the bottom level and goes decreasing on the upper level. This is due to the sediment settling phenomena and decrease in velocity of flow. The horizontal velocities at the end of the transition, 2 sections in descender, and at the end of descender are viewed. Figure 5, Figure 6, Figure 7, and Figure 8 respectively represents for the base case, modified case I, modified case 2, and modified case 3 respectively. The velocity in each case is seen decreasing while moving downstream. For the settlement of 0.20 mm particle, a horizontal velocity of 0.2 m/s is required, and the horizontal velocity obtained in numerical modeling at the end of basin ranges from 0.15 m/s to 0.22 m/s. 6 probes are defined at 3 different sections as shown in Figure 13 to view the change in Indiana velocity. The plot between velocity and time at those probes are shown in Figure 14, Figure 15, Figure 16, and Figure 17 for the base case, modified case I, modified case 2 and modified case 3 respectively. In all the cases it is seen that velocity converges toward fixed value with time, which reflects the stability of simulation. In all the cases, except case 2, the velocity at probe 1 and probe 2 is higher, as this is just after the transition length, whereas in case 2, the velocity in all probes is of similar magnitude. Figure 18 to Figure 21 represents the longitudinal sectional view of settling basin with sediment net change in height for the base case, modified case I, modified case 2 and modified case 3 respectively. The sections are viewed in the middle of each hopper. It is found most of the deposition has taken place just after the end of the transition. At the end of the simulation in the right hopper, the maximum deposition of sediments was found to be 0.97 m, 1.06 m, 0.99 m, and 1.32 m respectively for the base case, modified case I, modified case 2 and modified case 3 respectively. Similarly, in the left hopper the maximum deposition was 1.24 m, 1.19 m, 1.04 m, and 1.15 m respectively for the base case, modified case I, modified case 2 and modified case 3 respectively. It is supposed to settle sediment with a diameter of plus 0.20 mm by the settling basin of BHP. The 0.20 mm sediment particles are expected to settle with a velocity magnitude of nearly 0.2 m/s. It is found that the horizontal velocity distribution in the basin is less than 0.2 m/s. Therefore, the settling basin is operative for sediment size plus 0.20 mm. The trap efficiency for the range of sediment 1.00 to 0.25 mm, 0.25 0.180 mm, 0.180 to 0.075 mm, and below 0.075 mm respectively are 100%, 100%, 85.76% and 24.62% respectively. The overall trap efficiency of the settling basin obtained for about 3.5 hours, 12,460 SEC, is about 53.12%, whereas for particle above 0.20 mm is 99%. In the physical model, the trap efficiency for the range of sediment 1.00 to 0.25 mm, 0.25 to 0.10 mm, 0.10 to 0.075 mm, and below 0.075 mm respectively are 100%, 82.67%, 45.32%, and 23.88% respectively, whereas overall trap efficiency is 34.34% and for plus 0.20 mm is 87.66%. The comparison of trap efficiency between numerical and physical modeling is shown in Figure 22. The trap efficiency comparison between the base case and modified cases that are obtained from numerical simulation is shown in Figure 23. It shows the overall trap efficiency of modified case 2, i.e. transition angle 8 degrees, is better than the other cases. 4 conclusions. In this study, the flow velocity, particle distribution, and concentration of the sediment particles at different time intervals are studied for BHP. These parameters obtained from numerical modeling is used to obtain the trap efficiency of the settling basin with time. The following conclusion has been drawn in this study. 1. The velocity obtained for all cases for the particles greater than plus 0.20 mm is around 0.2 m/s, which seems good agreement with the value obtained from the empirical result. 2. The overall trap efficiency of the base case obtained from numerical modeling is 53.12% whereas physical modeling is 34.34%. Similarly, for case I, case 2, and case 3, the result obtained was 51.98%, 53.97%, and 50.52% respectively. 3. Among the cases, trap efficiency for case 2 seems a more efficient basin whose overall trap efficiency is 53.97%. 4. In the different cases run, the case doesn't have a dividing wall and it has lower trapping efficiency compared to other cases, although the deposition pattern with the base case is similar. Thus, the dividing wall plays a significant role in boosting the capacity of the settling basin. 5. It is recommended to conduct a couple of simulations with modification in the slope of the settling basin. The CFD calculation can deliver various useful information for obtaining trap efficiency and functioning of settling basin in hydropower projects.